Ooh, baby, let's rock. Ooh, don't make me pop this trunk. Ooh.
Hey, hope y'all are doing well. Before we get into the thick of this video, please make sure that you have in front of you a notebook and a writing utensil because I know you are all going to be taking very detailed notes on everything I put on the screen. So today we're actually going to think about combining some of the topics that we've reviewed earlier this week. We're going to be talking about energy in simple harmonic motion. And this is also going to include some brief review of how to draw energy bar charts. So first, y'all know I love graphs. We're going to talk about what a graph of simple harmonic motion looks like, and we're going to look at some key points and what they represent. This is a displacement versus time graph, and we see that this peak, our maximum displacement, that's going to be where our amplitude is. And as always, we have both positive and negative amplitude. So we have a maximum positive displacement and a maximum negative displacement. Wherever the graph crosses through the x-axis, right, that represents the point of zero displacement. So that's going to be our equilibrium. And these are the key points that we look at when we look at a graph of simple harmonic motion. Before we dive into looking at the key characteristics of our amplitude and our equilibrium points of motion, let's just remind ourselves how we actually identify the period from a graph of simple harmonic motion. So if this is displacement versus time, right, we know that the period of motion is defined as the time it takes to complete one full oscillation back and forth. So if we're thinking about a pendulum, it's going to be from the starting point all the way to the other side and then back to that same starting point again. So when we look at this graph here, we see that the easiest way to measure the period is to look at the time between one positive amplitude and the next positive amplitude, or if the circumstances are right, we look from one negative amplitude to one negative amplitude. So we see that from peak to peak here, that is going to represent our period, the time it takes to go from that first amplitude to the other amplitude and then back to that same amplitude again. Okay, so let's start by diving into what's happening at our amplitude. So at our amplitude, right, whether we're talking about a spring or a pendulum, that's going to be our point of maximum displacement. So that's where the spring is either compressed the most or stretched the most. Or for a pendulum, that's one of the peaks of motion on either side. The amplitude is defined as the point of maximum displacement for an object in simple harmonic motion. If we think about how we define potential energy, right? So in the case of a pendulum, we'd be thinking about gravitational potential energy. And in the case of a spring, we'd be thinking about elastic potential energy. For gravitational potential energy, wherever you have the most height is where you're going to have the most GPE. And if we think about EPE, right, that's where we're going to have the most compression or stretch of our spring, right? If we scrunch the spring up more, that's going to give it more elastic potential energy. So in both cases, we see that our potential energy, whether it's GPE or EPE, is at a maximum at the amplitude. In fact, all of our mechanical energy, our total mechanical energy, resides entirely in potential energy when we're at the amplitude. So there's no KE at the amplitude. There's no velocity at the amplitude. This is also the point where we have our maximum restoring force, right? So when we stretch the spring out really far, that spring force, bringing it back towards equilibrium, is going to be really strong. This is also where we have our maximum acceleration because this is the point at which the object is changing direction. So what's going on at equilibrium then? Well, equilibrium is defined as the point of zero displacement. So kind of intuitive, but at equilibrium, we have zero displacement from equilibrium. So all of that potential energy, right, which is entirely based on displacement, all of that potential energy at equilibrium has been converted to kinetic energy in both cases. So Now we have all KE and we have 0 PE, right? And this is also the point where we have our maximum velocity, which makes sense given that we have our maximum KE. We also have no net force at equilibrium and therefore no acceleration. So let's say we wanted to represent both of these points, the amplitude and the equilibrium, along the same motion with an energy bar chart. So if we have an ideal mass spring system or an ideal pendulum, so if there's no friction or other external forces, right, we know that our total mechanical energy has to stay constant. So at both amplitude and equilibrium, we have the same amount of total mechanical energy. The only difference is that at the amplitude, all of that TME is all of that TME resides, as I said earlier, in the potential energy. And then at equilibrium, right, the TME is the same because we're not losing any of our total energy, but all of the potential energy has been converted or transferred into kinetic energy.